All right, so 4.3, we've got linear independence. So if S is a vector set and it's non-empty and it's vectors from a vector space V, then if you set up this equation, right, so you take scalar multiples of each vector, you add it all together and you equate that to the zero vector, then surely this system has at least one solution. It's got the trivial solution, right? So each scalar, if you make each scalar zero, clearly it satisfies that equation. Now, right, so we know this is called the trivial solution. Now, if this is the only solution, then S is said to be a linearly independent set. So if there is any other solution other than only the trivial solution, then S is said to be linearly dependent. Right, so it's a simple definition. If you set up that system of equations, this equation, and the only solution is a trivial solution, then the set is linearly independent. If you find any solution other than the trivial solution, then that set is called linearly dependent. So that's a definition of linear independence. Right, so Theorem 1 then just takes everything we've said up until now into account. So if you've got a set S with two or more vectors, when is the set of two or more vectors linearly dependent? It's linearly dependent if and only if at least one of the vectors of S is expressible as a linear combination of the other vectors of S. Okay, so if you can write one vector as a linear combination of the other vectors. Okay, so I mean you can again visualize this. If you can write one, okay, so let's say you've got a set S of vectors, all right? Up until that, and let's say you can write, say, V1 as a linear combination of the other vectors in the set, okay? So you can find scalars K2 up until KR such that you can write V1 as a linear combination. Now, I mean, you can go and clearly see then that you can write V1 minus K2 V2 all right, minus up until minus KR VR, okay, is equal to the zero vector. Now look at your solution, right? So what's that value there? What's that value there? What's that value there? So essentially, you have the following. All right, so basically, what is the solution now? Is there a trivial or non-trivial solution? So you can let K1 be 1. You can let K2 be K2, whatever it is. And you can let KR be whatever it is. Is this a trivial or a non-trivial solution for my K values? It's a non-trivial solution because at least one of the Ks, which in this case is K1, is a non-zero number. Okay, so so the system is linearly dependent. Okay, because there exists a non-trivial solution. It's linearly dependent. All right, then going back, a set is linearly independent if and only if no vector in S is expressible as a linear combination of the other vectors in S. Right, so it means that your solution to this equation, right? Your solution to this equation, you're never going to find a non-trivial solution, because if you can find a non-trivial solution, it will mean that that you can, if you can find it will mean that the vectors are going to be linearly dependent. Okay, so that's going to force K1 to be 0. It's going to force K2 to be 0. It's going to force all your Ks to be 0. Right, so in this example, they ask us to test the sets S for linear independence. If we find that the vectors are not linearly independent, in other words, they're linearly dependent, then we're asked to express one of the vectors as a linear combination of the others. Right, so what do we need for linear independence, and what do we need for linearly dependence? Remember the definitions of linearly independence. Right, so let's check R3. Let's say S is given as the set of 3 vectors, and we are asked to check whether S is linearly independent or linearly dependent. Okay, so we're going to take, for my question 1, we're going to take scalars K1, K2, and K3 such that the following holds. Okay, so we need this to hold. We need this to hold. Now, what are these scalars K1, K2, and K3? For linearly independence, we need K1, K2, and K3 to be 0. For linearly dependence, we need at least one K1, K2, and K3. We need at least one of the 3 to be non-zero. Right, so the only way we can establish this is by actually going and solving for K1, K2, and K3. So we can set up 3 equations. All right, so there we've got our 3 equations. And now, so those are my 3 equations. And now I have to go and solve for the values K1, K2, and K3. Now, from K1, we can from equation 1 we can solve for K3 in terms of K1. So there we can solve for K3 as minus K1. Now, from the second equation, we can use the first equation and the second equation simultaneously and do substitution, and we can then go and solve for K2 in terms of K1. Right, so there we can solve for K2 as 3K1, and then we can use equation 3 and do the substitution, and we can go and further solve to get the following. Right, so basically from 3, right, so we can go and substitute for K2, we can go and substitute 3K1. For K1, right, so we can leave K1, and then we can substitute for K3. We can go and substitute minus K1. Okay, so basically, clearly that is satisfiable, right? So that, what does that tell us? So that's clearly satisfiable. So what does that tell us? It tells us that we can basically pick any value for k that we want. Okay. Right. So what we can do is we can pick. So basically we can pick we can pick K1 as 1. And if K1 is 1, then K3 is minus 1. And K2 is going to be 3. All right, so it follows. What does that tell me? It follows that that S is not linearly independent. Okay, so if it's not linearly independent, what is it then? It is linearly dependent. And we are asked to write one vector as a linear combination of the other vectors. Right, so how would we do that? Right, so therefore you can write that linear combination there. And right, this means that you can in actual fact, you can write the vector 1, 1, 4 as a linear combination of the other vectors. And it's in fact the linear combination 1 minus 2, 1, plus 3, 0, 1, 1. Okay, so that's the consequence of linearly dependence, meaning you can write the vectors, one vector as a linear combination of the other vectors. So to answer the question, no, those vectors are not linearly independent. They are linearly dependent. All right, the next question here is they ask us to show linearly dependence or linearly independence for that set S. Now, what is P2 again? P2 is what? What is P2? What is P2? P2 is the set of all polynomials of degree bigger or of degree less than or equal to 2. All polynomials of degree less than or equal to 2. And we are asked to show in that vector space whether S is linearly independent or linearly dependent. Okay, now sometimes these problems are easily done just by normal inspection. So you can actually look at inspection. So what we can say is, we observe that, right, so we can take minus 7 times the first polynomial, okay, plus 2 times the second polynomial, right, plus the third polynomial. Right, okay. Okay, now what is that equal to? So minus 7x plus 4x plus 3x, that's going to be 0. Minus 2x plus 2x, right, that is going to be 0. Okay, so that's going to be 0. So now the question is this linearly dependent or independent? So you've got minus 7 there, you've got 2 times that polynomial, and there you've got 1 times that polynomial. So is it linearly dependent or linearly independent? Okay, so it's easy to see. All right, so the set S is linearly dependent. It's linearly dependent, and specifically right, you can write x, well, you can write the polynomial x. You can write the polynomial x as 2/7 of the polynomial 2x minus x squared, okay, plus 1/7 of the polynomial 3x plus 2x squared. Okay, so yes, this is a linearly dependent set, and you can write one polynomial as a linear combination of the other polynomials. Okay, so now let's look at the third one here. There they ask us, establish whether or not that set is linearly independent. So what is f minus infinity, positive infinity again? It's all functions, real valued functions defined for all x from negative infinity to positive infinity. So we are given two functions there, sine x and cos x. Now, is that set linearly dependent or linearly independent? All right, so we take 3, so we take k1 and k2, and we let them be scalars, such that, let's see what happens. Take k1 times sine x, and add that to k2's cos x, and let that be 0. Okay, now this has to be true for all x's. For all x between negative infinity, positive infinity, that has to hold. Can you find scalars k1 and k2 such that for all x, k1 sine x plus k2 cos x is equal to 0? That's the question. Right, so right now, what happens if k2 is not 0? Right, then, so then for, if you make x pi over 2, we have, so k2 is not 0. Let's, no, let's rather take, let's take not x pi over 2, let's take x to be 0 degrees. We have then that k1, what is sine of 0 is 0, plus k2, what is cos of 0 is 1. And that has to be 0 because remember it's for all x. So therefore k2 is equal to 0, so contradiction. All right, so therefore k2 has to be 0. All right, so now, all right, if k1 is not 0, then, right, then for x pi over 2, we have then that k1 sine pi over 2 plus k2 cos pi over 2 is equal to 0, which is then going to imply that k1 sine of pi 2 is 1 plus 0 is equal to 0, which is going to mean that k1 is 0, which is impossible. So therefore k1 must also be 0. Alright, so as k1 is equal to k2 is equal to 0, S is linearly independent. Linearly independent. Because I cannot find a non-trivial solution to that scalar equation. I cannot find somewhere a non-zero k1 or a non-zero k2 that satisfies that equation. I can only get zeros for the k1s and k2s. Linearly independent. All right, so the number 4, we are asked to show that whether this set is linearly dependent or linearly independent. And this set S is a set of matrices. And these matrices are 2 by 2. They're from the vector space M22. So again, what we need to do is we need to find scalars K1, K2, and K3 such that the following holds. Okay, so let K1, K2, K3 be scalars such that K1 plus the first matrix plus K2 times the second matrix plus K3 times the third matrix is equal to the 0 vector. And what's the 0 vector in M22? It's the 2 by 2 0 matrix. Okay? Right? So, okay, so how do we, well, we can quickly see, if you look by inspection here, you can see there, there's a 0, there's a 0, there's a 2, and there's a 0. So we can quickly go and solve for K3. Right, so we can quickly go and solve for K3. So from there, right, so from there we've got that 0K1 plus 0K2 plus 2K3 has to be 0. So that's from matrix addition, which implies that K3 absolutely has to be 0. Okay, now we can solve for K1 as well. So we also need minus K1. Remember now, observe this, there, and there. Okay. Right. So so from there we can solve for minus K1 plus 0K2 plus K3, which we know is 0, is equal to 0. So from there, K1 is 0. Okay? Okay, now also observe this. There we've got there and there and there. Okay, so we can find another equation there. And that equation is, right, so we can also say that right, so minus, minus K1 minus K2 plus 0K3 must also be 0, and we know K3 and K, we know that they are all zeros, so K2 must also be 0. Okay, so what have we now established? We've established that K3 is 0, K1 is 0, and K2 is 0. So is this set of vectors linearly dependent or linearly independent? The set of vectors is linearly independent. All right, so therefore, all right, so we can say hence S is linearly independent. All right. Right, so linearly independent, it's we've solved our scalars, so that set is clearly linearly independent. All right, so theorem 2 is theorem 2 is it's an important theorem in the sense that it tells us a little bit more about the relationship between a set that has more vectors than there are components within the vector if the vector is from Rn. Theorem 2 states that if S is a set of R vectors and it's an Rn, now we know what Rn is. It's the set of n tuples where the vector addition is component-wise and scalar multiplication is component-wise. Now, if it happens that now each vector in Rn has n components, right? So if the number of vectors in S is bigger than the number of components of the vector, of the vectors, then S is linearly dependent. Okay, now it's interesting to try and answer this question. Why is it the case that if you've got more vectors in your set S than you have a number of components, why does it then mean that S is linearly dependent? So we need to, what's interesting here is the relationship between this problem and what we've done in matrices, solving linear systems. So let's go and investigate why this is the case. All right, so what I'm going to do is let's take the set S and look at each vector. Right, so if we look at V1, because V1 is an Rn, that's the form of V1. V1 is an n tuple, and there are the entries of V1. The entries of Vi is generally given by that vector, and the okay, so now remember we consider the set S and we look at each vector in the set S. So there vector V1 is an n tuple, can be represented in that way. The ith vector in S looks like that, okay, and then the rth vector in S looks like that, okay. So now what we want to do is we want to check whether or not this set is linearly dependent or independent. Now let's take R to be bigger than N and see what happens. All right, so what we're going to do is we're going to, let's assume R is bigger than N. Okay. Now, the R is that R there, and the N is that N there. Okay. Right, so what will happen if R is bigger than N? So we're going to start off with scalars. So we're going to let, again, let K1, K2 up until KR be scalars, right, such that, so now you've got your, you compose your sum V2 plus, okay, you get your ith Vi, right, plus up until your rth vector Vr, and you put that equal to 0. Now to check whether we have linearly dependence or independence. For linearly independence, we need to show that it doesn't matter what I can take any K1 up until KR, these quantities are always going to be 0. The only solution to this equality there is when all those scalars k1 up until kr, they must all be 0. For linearly dependence, we need to show that at least one of those scalars somewhere there's a non-zero scalar. If there's a non-zero scalar, we've got immediately linearly dependence. So to prove this theorem, I don't need to now show that there's linear dependence. In other words, I can find some non-zero k somewhere such that we've got this equality that's satisfied. All right, so now what I'm going to do now is I'm going to take V1 and I'm going to substitute it in there, right? Then I'm going to do that for all the V's. I'm going to take VI and substitute it in there, okay? And then I'm going to take VR and substitute it in there. And I'm going to do it for all the V's, right? So what I get on the left-hand side is basically a sum of n tuples, and on the right-hand side I've got an n tuple. And in actual fact, I just forgot to mention that that's not the number 0, that's the vector 0. Okay, so let's see what this looks like. Alright, so as I explained, so where you see a V1, you substitute the vector V1. Okay, so you've done that. Where you see a VI, you substitute the vector VI as we described it previously. And where you see a VR, you substitute that whole vector there. Okay, and that has to be equal to the 0 vector. Okay, so let me just make that so that you guys don't think that's the number 0, it's the 0 vector. Okay, so that we have then is equal to this whole 0 vector. So now you set up a system of equations. So basically, right, so you can use scalar multiplication here, and you can multiply the scalars in there, and then you can set up the following system of linear equations. All right, so there we've set up our system of linear equations. Okay, and again, what you do is your first linear equation you set up according to the first component there. You equate that to 0. Then the second component, you equate that to 0, and you carry on and you keep doing that until you've set up a system of linear equations, as we've done here. Okay. Now the question is, how many unknowns are there in this linear system? First of all, what kind of a linear system is this? It's a homogeneous linear system. And how many unknowns are there? Well, we've got 1 unknown, 2 unknowns. There are unknowns, and how many equations are there? Right, there are n equations. If you go and count, all of that, there are n equations and are unknowns. All right, so this is a homogeneous. It's a homogene. This is a homogeneous linear system. It's a homogeneous linear system with R unknowns and n equations. And we said that R is bigger than n. Now, what do we know about a linear, homogeneous linear system that's got more unknowns than equations? It means that you're going to have infinitely many solutions. All right, so there are infinitely many solutions to this system because it's a homogeneous linear system that's got more equations than, more unknowns than equations. So if there are infinitely many solutions to this system, it means you can get many different solutions for the scalars k1 up until kr. Right. All right, so there exists non-trivial solutions. There exists non-trivial solutions for the scalars k1, k2 up until kr. Because remember now, this linear system has got infinitely many solutions, so we can find a non-trivial solution for k1 up until kr. Now, a non-trivial solution means that at least one of the k's is going to be non-zero. So you cannot then conclude that the system is linearly independent because we can find a non-trivial solution. So therefore S is linearly dependent. Okay, S is linearly dependent. All right, now if we go back to this theorem, if you look at the example, so there we need to decide whether the following sets are linearly dependent by inspection. So if you look at the first set, is that set linearly dependent or independent? Now, if you go back to your theorem here, your theorem states that if you work in Rn, in this case we work in R2, okay, so n is 2. Now, if the number of vectors in your set is larger than n, and the number of vectors here in the set is 3, okay, so it's the number of vectors is 3, so R is 3, and n is 2. Right, so 3 is bigger than 2, so we can therefore conclude that S is linearly dependent. So that first set clearly is linearly dependent. The second one, here we are given R3, so R is 3, okay? And the number of vectors in your set is 3. Right, so again, we can't use this theorem because this theorem specifically states that R needs to be bigger than N. In this case, R is equal to N, so we can't use that theorem. So we need to find some other way to check whether this is linearly dependent or independent. But you can quickly see by inspection that, that 5, 7, and 9 you can write as 1, 2, 3 plus the vector 4, 5, 6. So what have we shown? We've shown that this vector here is a linear combination of these two vectors here. Right, so so basically we can then conclude that that set of vectors is linearly dependent. So why is that? All right, so remember we said that 5, 7, 9, remember we said that you can write that as the vector 1, 2, 3 plus the vector 4, 5, and 6. Okay. So again, guys, you can write this as, you can write that as 5, 7, 9, okay, minus the vector 1, 2, 3, minus the vector 4, 5, 6 is equal to the vector, the 0 vector, okay. So now, so what are your k values? So in this case, your k1 is 1, your k2 is -1, and your k3 is also -1. So the equation, this equation that we originally set up, right? This equation that we originally set up, does it have trivial solutions for the k's or non-trivial solutions for the k's? For the trivial solution for the k's, all your k's need to be 0, and it always needs to be 0. You cannot find non-trivial solutions. So now the question is, this system here that you normally set up to check for linearly independence, here I have demonstrated that you can find non-trivial solutions for the k's. So as soon as you find a non-trivial solution for the k's, you immediately have linearly dependence. If you find only the trivial solution, you have linearly independence. If you find non-trivial solutions, you have linearly dependence, and if you have a trivial solution, you have linear independence. Alright, so basically Theorem 3 states the following. It says that if a set containing 0, or rather a finite set containing the 0 vector is always linearly dependent. Number 2, a set with one vector is linearly dependent if and only if it's the 0 vector. And number 3 is a set with two vectors v1 and v2 is linearly dependent if and only if one is a scalar multiple of the other. Right, so let's go and see why this is the case. Let's look first at 1. If you have a finite set containing a finite set containing the 0 vector is linearly dependent. Why is that the case? Okay, so let's look at this. All right, so 1. Okay, so let S be a set that contains the 0 vector. All right, so we're going to define S as just set the 0 vector v1, v2 up until vr. Okay. Now to check linearly dependence or independence, we take our scalars. Let k1, k2 up until kr plus 1 be scalars such that k1 0 vector plus k2 plus and that needs to be the 0 vector. Right. Now, if you look by inspection, if you look at all these cases, K1, K2 up until KR plus 1, can we find a non-trivial solution to this system? Okay. So it's easy to see the following. Note that we can make K1 1 and we can make K2 0 and we can make all the K's 0 except K1. You can make KR plus 1 0. Okay, is a solution, is a non-trivial solution. It's a non-trivial solution. So the system is it linearly dependent or independent? Is a non-trivial solution. Okay, so basically, write the system. The system is it's linearly dependent. It's linearly dependent. All right. All right, next we have number 2. A set with one vector is linearly dependent if and only if the vector itself is the zero vector. Okay, so again, you start off with let S be a set with a single vector. Okay, now if S is linearly dependent. If it's linearly dependent, then if it's linearly dependent, we can find a solution to this equation. For some, we can find a non-trivial solution. So we can find some non-trivial, we can find some non-zero k such that k1v is the zero vector. Okay. Now we did a theorem which said that if the scalar multiple of a vector is the zero vector, then either the scalar is the zero or the vector itself is zero. So hence v is the zero vector, right? And again, I can't remember exactly what the theorem was, but go back to your notes. I think it was in section 4.1. That if the scalar multiple of a vector is the zero vector, then either the scalar is the zero or the vector itself is the zero vector. Right, now let's look at the other way around. If v is the zero vector, if v is the zero vector, then let k1 be 1. Then if you look at the scalar multiple, if you look at k1 v, right, that is 1 times the zero vector, and we know from previous theorems that a scalar multiple of the zero vector is the zero vector. Okay, so it follows that the set must be linearly dependent. So it follows that that S is linearly dependent. Okay, and why is it linearly dependent? Because I have just found a non-trivial solution to that equation. K1V equals 0 has a non-trivial solution. I can just make K1 equal to 1. I can make it anything I want it to be. So therefore S is linearly dependent. Okay, so again, let's look at the third one. So you've got two vectors, are linear, a set of two vectors linearly dependent if and only if one is a scalar multiple of the other. Okay, so let's S be V1, V2 and assume S is linearly dependent. So now we need to prove that V1 or one vector is a scalar multiple of the other vector. Alright, so assume S is linearly dependent. So let's choose K1, K2 be scalars such that, alright, so let K1 and K2 be scalars such that this equation holds, but specifically we choose the scalars, we choose a non-trivial solution. So we can say such that this holds, and either K1 or K2, let's say K1 is non-zero. Okay, why can we do that? Because we said S is linearly dependent, so we can find a non-trivial solution to this equation here for the k's. So we can find a non-zero. At least one of the k's is going to be non-zero. Let's say K1 is non-zero. All right. So then you can write K1 V1 as minus K2 V2, which then will imply that you can write V1 as minus K2 divided by K1, because K1 is non-zero. All right? Okay, and so that implies that you can write V1 as a scalar multiple of V2. Okay, so you've proved your theorem. So now you have to prove it the other way around, because it's if and only if. So let's assume that V1 is a scalar multiple of V2, and then we have to show that S is linearly dependent, but it's easy to do that. Alright, so let's assume now that V1 is a scalar multiple of V2, so you can find a K such that V1 is KV2. And now we want to show that our set S is linearly dependent. But this, again, is not difficult to do. It's not difficult to do. Alright, so I just need, okay. So there we go. So this implies that we can write V1 as, we can go and rewrite that equation as the zero vector. Okay, so from this, we can let K1 be 1, and we can let K2 be minus K. All right, now what does that tell us? What does that tell us? Right, so hence this system here has got a non-trivial solution. This system here, it has a non-trivial solution. It has a non-trivial solution. And what is that solution? The non-trivial solution there is the solution where K1 is 1 and K2 is whatever that minus K is. Okay, and this is a non-trivial solution because that's non-zero. So hence S is linearly, it's linearly dependent. It's linearly dependent. Okay, now if we go and apply this, look at this example of the following sets: linearly dependent or linearly independent. Well, the first one there is go and look at the set 0, 1, x, x2 in P2. What is P2 again? It's a set of all polynomials of degree at most 2. And what is the zero vector in P2? It's the zero polynomial. The zero vector in P2 is the zero polynomial. So therefore, S has got the zero vector. So now this number 1 tells us if you have a finite set that contains a zero vector, then that set is linearly dependent. Okay, so 1 is clearly S is linearly, it's linearly dependent. It's linearly dependent. Right? Okay, by our theorem. Number 2 is there we've got S in C minus infinity, positive infinity. Now again, I want you to go and look at the definition of C minus infinity, positive infinity. All right, so there we've got functions sine 2x and sine x cos x, and we are asked to basically establish whether that set is linearly dependent or linearly independent. Now, what you can do there is so you can observe that. Right now we have that sine law, sine 2x. We know is 2 times sine x cos x. Okay, so we've shown that sine 2x is a scalar multiple of the other vector in the set. So this theorem states that if you have a set of 2 vectors and the one is a scalar multiple of the other one, then my set is linearly dependent. Okay, so if one is a scalar multiple of the other, then it's linearly dependent. So by theorem 3, S is linearly dependent. It's linearly dependent. Okay.